Okay. All right, we are now recording. I wanted to go a few more announcements before we get going. Okay. The Ambers came in together. Okay. And then one left right away. Okay. All right. So we went from volleyball to basketball, but we'll manage. Okay. The last few announcements have to do with end-of-term issues, okay? First and foremost, have you done the student course evaluations? Not yet, okay? Please don't forget to do those, okay? Yeah, double negative there, okay? But please don't forget to do them. Please do them before you leave for the term, okay? And you can't wait till the very end to see how bad it is, before you do them. But please don't forget to do those. Okay. Secondly, let me talk briefly. Today is regular class day. It's the last regular class day, meaning it's the last day I'll accept the paper, which I've got one in this morning already, without you losing points. So if you haven't turned in the paper yet, please get that in today if you can. Tomorrow I'll be on Birmingham campus, but if that's inconvenient for you, you can slide it under my door on this campus, and I'll pick it up Monday. If you have to, and to work on it over the weekend, turn it in as early in the week as you can rather than late in the week, please. Okay, but you will lose points anything after today. So, now, office hours today then are normal, 10:45 to 1:15. My 1:15 class, it's going to be hard to judge. That may not take the full 4.5 hours today because we are winding down. We're on the last chapter, and if we finish the chapter, we may start the lab, and then it may be we'll be here 4.5 hours, but it may be they'll be done a little early. And they also have a test to take on the last chapter. Okay. So yeah, we could be here the whole time. I forgot about that. So yeah, we probably will be. I was going to say I may have more office hours later in the day, but maybe not. Tomorrow, my office hours on the Birmingham campus are usually 7:45 to 1. However, tomorrow I've got to leave about an hour early. My wife is flying to Amsterdam for a week's professional meetings. Oh, poor gal, and and I need to get her to either we're going to leave for the airport at 1 or I need to get her to the airport by 1. I can't remember which way it is. I'll find out tonight, I'm sure. So I'll probably have to leave Birmingham campus 15-ish or something like that. So I'll be leaving a little early. Every night this week I've been here late, so I don't worry about losing that hour. But it's just at an office hour you won't be able to catch me. Okay, but you will be able to catch Ryan because he came in. Okay. All right. Now, that said, next week is finals week, mostly. Okay. I do have a second mini-term class, that one I'm talking about today. We have class then on Tuesday as well. Okay. So anything we don't finish today, we're going to be finishing on Tuesday, and they'll have their last test on Tuesday. Okay. So I will be in class then. But otherwise, it's finals. Mondays and Wednesdays, I have all upper-level classes, as in linear algebra, calculus 1, calculus 3, and differential equations. And all of those classes have take-home finals. So I won't be administering a final on Monday or Wednesday. I'll be receiving them. So basically, Monday and Wednesday, I'll be in my office 7:45 to 5:15. Okay, Monday and Wednesday of next week. Okay, Tuesday, like I said, this class has a final 8 to 10, basically. It's 8 to 9:50 technically, but if you need more time, I'll be here as long as you need me to. I don't have another final that day, but I do have the class at 1:15. That's the last class for the second mini-term course. Now, see, the class that follows this one, their final would have been on Tuesday. On Thursday. So, all right. So I will be in class then. That class, that Tuesday, almost definitely will not last 4.5 hours. There will be no lab, I don't think, that day, so at least the last 2 hours will be free because, I mean, we're already finished all the material. That is, if we finish and have the lab on today. If we don't, then we'll have the lab on that day. But I still think they'll be through before 4.5 hours. So that day I will be in the office later, but not. Terrell is here. There you are. It will not be. I won't be in class as long as that's almost guaranteed. Okay. I already talked about Wednesday. Thursday is when I give the final for that afternoon class. But it's not going to take long. So probably they'll start around 1 or 1:15. I bet you they're all going by 2. It's not going to be a very long final at all. Unless some of them are having to make up stuff, but they should get that done on Tuesday. So I will have more office. So basically Tuesday and Thursday I'm here 7:45 until 6 o'clock in the evening, but the class times and lab and test times and stuff will alter that a little bit. Okay, then on Friday of next week, I will be here the full time on Birmingham campus, 7:45 to 1. Now, that's it for y'all, okay? You probably will be finished sometime next week when you finish all your finals. We will be here the following week, all week long. I don't know why they have a whole week of duty days for us, but they do. The grades are due by Wednesday, probably noon. This is the week after finals. Now, that means if you have something you're going to get to, and I talked with Natalie, okay, earlier, and we worked that. You can, if Tuesday morning at 8 is not good for you on the final, anytime next week will be. With the understanding, Friday I'm on the Birmingham campus. So if you are going to go to Birmingham campus Friday and take your test, you got to let me know that ahead of time, because otherwise there's not going to be a test over there. Okay, so please let me know if you are planning to do that. So, but that following week, I'll be here Monday and Tuesday. Monday, probably 7:45 until 5:15. Tuesday, probably 7:45 until 6. Wednesday, that's when grades are due, and I'll be here 7:45 to 5:15. But then that sometime on Thursday, we have to leave town. This is probably what you were hearing. This is the week after finals. I mean, grades are already in, everything. It's just a duty day. But in case you're looking for me, we have a graduation in LSU that Friday, so we got to drive down Thursday. I don't know what time we'll be leaving, but I might be here for a short time and then leave, or just not be here at all. Friday I won't be here at all, and unfortunately I will miss graduation on Saturday. We'll be driving back from LSU then. Are any of you graduating? Okay, sorry, I'll miss seeing you, but so congratulations ahead of time. Sorry about that. I don't usually miss, but we actually have 2 graduations this time. The next, I said that, yeah, the previous Friday, like at the end of finals week, we have a niece graduating from Auburn, and but that will be on Saturday, so we can leave on Friday evening or even Saturday morning and get down there in time for that one. So that won't interfere with my office at all. Okay. Any questions there? One other thing, please, if you are going to register for summer classes, please do so. I was trying to register a student yesterday. They have canceled classes right and left. So they're going to continue doing that. So if you haven't registered yet, please register before they cancel the class you want to register for. So someone got a burr under his or her saddle last summer, and they are really being strict with it this summer. I mean, I think. Yeah. several years ago they did allow it, then they quit allowing it, and then I heard rumors that they're going to reinstitute that, maybe in a slightly different way. But check with financial services. Now, you know, all the scholarships I was telling you about earlier, that was geared for that. So if you can't get the Pell Grant, you could, but check with financial services, because I don't know the answer to that. Yeah, sorry. They'll be glad to let you know. Okay. Any other questions before we get started today? Sorry, I've taken probably too long with that. Well, I can't get the slideshow to come up. There we go. Well, I thought we were going to. There we go. Okay, now we did example 6, and we started example 7. What we didn't have time was to do example 8. Okay? So if there are any questions, and this is on chapter 3, exponential and logarithmic functions, 3.1, exponential functions in their graphs, and that's what we're doing in 7b. On page 204, we're doing an exponential function, we're graphing it. So that's not this function. Let me get my pen activated for the darker color. Okay, here's our function. G of x is equal to 1/2 e to the minus 5/8 x minus, I'm sorry, 0.58 x. Okay, keep saying 5/8. 0.58 x, which is 58/100 of x. Okay? Finally, I said it right. Now, how would you go about graphing that? Maybe you'd first draw a graph. Okay? And then, because of the exponential function, we know it's not negative unless there's a minus sign in front of it. Flipped it across, there's not. So we'll put our axis down there. We'll pick a few points. 1, 2, 3, 4, 5, 6, 7, 8, 9. Negative 1, 2, 3, 4, 5, 6, 7. Positive 1, 2, 3, 4, 5, 6, 7, 8. Okay. How would you begin? Second? Okay. Give me a number. 0, my favorite. Okay. Not you. I mean, okay. All right. What do you get when you plug in a 0 for x? Negative 0.58 times 0 is 0. E to the 0 is 1. 1/2 of 1 is 1/2. Okay, 0.5. There we have it, right there. There's our first point. The rest of these, I guarantee you'll need a calculator, okay? That's the only one I can pick off at the top of my head. So pull out your calculators. And by the way, I said this last class and probably several before, please bring your get to know your calculator. Get on good terms with your calculator. So you and it are one. You know, you just think alike, okay? So you don't have to learn the calculator when you're trying to take your final, okay? So give me another x. 1, okay, I like it. Okay, clever you come up with that one. Okay, what's negative 0.58 times 1? Negative 0.58. Then do e to the negative, well, and you can do it on your calculator however you want to. But you figure it out and tell me what the answer is. When x is 1, what is your y? Please, folks, don't forget to bring a calculator Tuesday, because I only have 2 that work anymore. One's my personal one. I don't mind you using that. The other one is a cheapie that doesn't do exponentials, so not going to be a lot of good on this test. So, by the way, let me say this too. I forgot to say it. The test consists of 2 parts. The first part is the Chapter 3 test, which is going to be very short and very sweet, okay? Hopefully not too bad at all. And then the comprehensive part will cover questions in Chapter 1, Chapter 2, and a few in Chapter 3. Yes?
Did you say we get to drop our lowest test?
Your lowest test score. The lower quiz score and the lower test score. Yeah. Okay? Now, let me also say this. How I'll do the final. I'll try to come up with 10 questions from Chapter 3. They'll be pretty easy, straightforward, okay? And I think you'll find you can get a pretty good score there. Number 2, the final will probably have 4 questions from Chapter 1, 4 questions from Chapter 2, and 2 questions from Chapter 3. Because we aren't doing too much on 3, okay? So I'll try to hit basic kind of stuff. They won't be the same questions you had on tests, but they'll be similar to those questions you had on tests. So that's why when I return the materials to you at the end of class today, then those are good things to review and study. Now, I was going to do it in the first class, but not everybody's been able to finish everything. So I'll do this at the end of class. And if you have questions on any of those that you don't know why you missed something, come see me. Later today, office hour 10:45 to 1:15. Maybe late today, after that 5 or something like that, possibly if I'm through with the lab then. And then tomorrow on Birmingham campus, anytime on Monday, I'll be in the office 7:45 until 5:15. So plenty of times to come ask me questions and clear stuff up. All right. Did anyone put that in your calculator? What you get? 1.29? 0.29. I can buy that. 0.29, that's a little bit more than a quarter. Okay? Give me another X. I feel like a cheerleader. Give me another X. 2, okay? 2 times negative 0.58 is negative 1.16, right? I think that's right. Yeah. And e to the negative 1.16, and then half of that, what do you get there? You can enter in your calculator whatever is the best way for your calculator. I just don't know your calculator. So. And if in the process of doing this stuff you don't get the same answer as somebody else, ask me. I can sort of maybe help figure out how to work it on your calculator. That's why it's a good idea to bring calculators. Okay, and get to know them. What you got? Anyone got it yet? No, it's going to be that hard. Okay. It looks like most of you have pretty advanced calculators. I may be wrong. So let me just, sort of like that example you see up there, let's do it. I would do a 0.5, that's 1/2. That's the easiest way to do 1/2. 0.5, then press the e to the x key, then press the negation key. Now that's not the subtraction key, it's the one in parentheses, not just the subtraction, okay? It's the negation key. 0.58, and I think all you have to do is then put 2, because that's what we chose. No, 0.58 times 2, yeah, you have to put times 2, and then press enter. 0.15 what? 7. So there you're even closer, between 1/10 and 1/20. I think we got a general idea where it's going to the right, don't we? It's approaching 0 and getting closer and closer to 0, but never getting there. So let's go to the left, okay? How about a -1? What would you press then? 0.5, e to the x, and minus a minus is plus 0.58. So you don't have to do a plus, just 0.58. Enter. Second. 0.893. So at -1, we're up here between 8/10 and 9/10. Okay? How about -2? So let's do it this way. 0.5 e to the, and since it's a minus, forget about the minus. The minus and minus is plus. 0.58 times 2. Enter. 1.6. Say again? 1.6. Okay. 1.6. -2 is a little over 1.5. Okay. Looks like a trend going here. How about -3? 0.5 e to the x. The minuses cancel out. So do 0.58 times 3 equal. Anyone get it yet? 2.84. So between 2.8 and 2.9, somewhere up there. How about -4? This is going so nicely. 0.5 e to the, and since the negative times negative is plus, don't do a minus sign there. 0.58 times, what do we say? 5 point what? 5.08. Just more than 5. 1, 2, 3, 4, 5. Somewhere right about there. Okay? That was 1, 2, 3, 4. So let's do a 5. 0.5 e to the 0.58 times 5. Those are minuses cancel out. 9.08. 1, 2, 3, 4, 5, 6, 7, 8. Somewhere off scale there. So we finally did it. We went off scale. That's what we're looking for. There's what that looks like. Make sense? Okay. A reminder, when you have a positive exponent here, your function's increasing. Okay? I think that's Jonathan, if I recognize him. Okay? All right. They generally go like this. When you have e to the negative power, it's going like that. Always decreasing for negative, always increasing when the argument here is positive. Okay? So that makes sense. Never negative, approaches 0 but never gets there. That's an exponential function. Now, a couple of things. This smaller coefficient here, the negative makes it go this way. The small one sort of flattens it out some. Normally exponentials come down much sharper than that. That's what doing that. The 1/2 then cuts that again. That's this is a horizontal. Okay, you got it. Yeah. It's a reflection across the x-axis. That's what the negative does for. I mean the y-axis. That's what the negative does here. The 0.58 is a horizontal stretch, so let's stretch it out here, which tends to flatten it. And this is a vertical shrink, which also tends to flatten it. But it's still an exponential, so it's going to take off in some time. Okay, good deal. Any questions on that? You'll see in the book, their picture is not quite as pretty as ours, but close. Okay. Any questions? There is a checkpoint. Not a bad idea to do your checkpoint. Now I think we're ready, if there are no questions, to move on to applications. One of the most familiar examples of exponential growth is an investment earning continuously compounded interest. I don't know, my credit union, back when I first entered way back, I think they compounded quarterly, okay? Then they got to compounding monthly. Now, it doesn't make a huge amount of difference, but a little bit. I'll take any bit. And then, after a while, they went to, I can't remember now if they're daily or continuously, but every time gets you maybe just a little bit more money. Okay? Now, this is the formula if your interest is compounded n times a year. Like quarterly would be 4 times a year. Monthly would be 12 times a year. Daily would be 365 times a year, okay? This would be the formula you use. The amount that you have is the principal, that's how much you put in there, times 1 plus the rate. Right now the rate is so incredibly small, it's amazing, saddening. There's Alexis and Allison, okay? And so this is something like maybe 1% or 0.5% or something. It's incredibly small now. Divided by that n, so that makes that a pretty small number, but you're raising it to a very large exponent. Okay, in that formula, A is the balance in the account, the amount you have, P is the principal, original deposit, what you put in there, R is the annual interest rate in decimal form. So if it's 2%, it would be 0.02, okay? N is the number of compounding per year, 4 for quarterly, 12 for monthly, 2 for semi-annually, 1 if it's annual, so you just don't even mess with the N then. 365 if it's daily, you know, that's what it would be. And T is the time in years, okay, not in months or days or anything else, in years, okay? Now, it's a pretty messy formula, but it's doable. They get computers to do it. They don't worry about it. But using the exponential functions, you can develop this formula and show how it leads to continuous compounding. Suppose you invest a principal P at an annual interest rate R compounded once a year. Then this would be it. Remember, you have P times 1 plus R, raised to 8. But you're only going to do it 1 year. So it's the principal plus your principal times the rate. That'll give you a new principal 1 year later. Okay, that's all that equation says. P times 1 plus R, raised to the 1 power. Okay, all. Okay, that would be your new balance. Okay, that's not a sheet. Okay. Now, if you continue doing this, and again, it's annually, so you don't have any N here. That's a 1. So then the next year, you would have whatever you had at the end of the first year times that same amount, which would be what you had here times the amount. So it would be P times 1 plus R squared. This would be P times 1 plus R to the cube. And you keep going. So after T years, it would be P times 1 plus R to the Tth power. Okay? And that basically is the formula we had before. Okay. Why they're doing all this now. To accommodate more frequent quarterly, monthly, daily, or whatever compounding of interest, let N be the number of compoundings per year, let P be the number of years. Then the rate per compounding is R per N, because you're not compounding, if you're doing it quarterly, you're only doing a quarter of that rate but 4 times a year, so that's why the account balance would be this. That's the formula they gave you to begin with. So why we went through all that to get there, there's that formula. When you know the number of compoundings increases without bound, then the process approaches what is called continuous compounding. If this N is getting smaller and smaller, bigger and bigger and bigger and bigger, and that is getting bigger and bigger and bigger, you're approaching something which is this. Formula for N compoundings here, let M equal N over R, which, this is rather bizarre. Goodness gracious, what a weird way to do this. If you notice this is M equal N over R, well then this is 1 over M. So why they went through this step to get there, I'm not sure. But here you still have MR, because R that was here, N that was here was M times R. So this N here becomes M times R. This is rather bizarre. Pull out the M, and you have P times 1 plus 1 over M to the M power times RT. So, we'll say this. That is exactly what an exponential is. 1 plus 1 over M to the M is your E. That's how we get it, okay? And if you started plugging in some m's here, of course with 1, if you plug in m as 1, this would be 1 plus 1 to the 1. That would be 2. Plug in 10 there. 1.1, that's 1 plus 1 raised to the 10th power, you get this number. So the 100 would be that number. 1,000, 10,000. See, it's going up, but really, really, really slowly. But 10 million, that would give you this. The higher you go, the closer you get to your E. If any of you have your calculators, do E to the 1 on your calculator. Press the E key. When it opens the parentheses, put 1. Hit enter. And what do you get? Okay. See, you're getting closer and closer to that number E. You keep going up in here, you're approaching E. So, look at the simple formula you get for continuous compound. A is equal to P E to the RT. That's it. Almost looks like PERT, doesn't it? Okay, no. Okay. P E to the RT. Now, it doesn't give you a lot better than daily, but it gives you a little bit better. Okay? And it's so much easier to do. So here are the formulas for compound interest. After T years, the balance of A in an account whose principal and annual interest rate are in decimal form given by the following formulas. For N compoundings per year, A is equal to P times 1 plus R over N times NT. Okay? All right. That's a bulky formula, but doable. Computers do it really nicely. Look how simple it is for continuous compounding. A is equal to P E to the RT. You got all the same thing, your principal, your rate, and the time. Now it's continuous, so you don't need the N anymore. There it is. Okay? So, you invest $12,000. Congratulations, you got $12,000 to put away, okay? At an annual interest rate of 3%. Congratulations there too. Find that somewhere today and I'll want to become your friend, okay? Find the balance after 5 years when the interest is compounded quarterly. So what would be the formula for that? P is equal to, this is example 8, right? Yeah, okay. P is equal to, how does that one go? I'm sorry, not P. A is equal to. Okay. A is equal to what? Okay, 12,000, that's your P, times, okay, 1 plus 0.03, very good, put that in decimal form, divided by, second? No, 4 quarters. 4 quarters in it. Okay, good morning, Vietnam. Okay, all right. Okay, raised to the 4 times 5. That's where the 5 comes in. Okay, that would be 20, right? N-T. N is 4 and T is 5, so 20. Okay, pull out your handy dandy calculators. And I'll walk you through this one too. 12,000, nice big sum, times open parentheses, 1 plus 0.03 divided by 4, close parentheses, then use the caret key. On most of your calculators, it's going to be the caret key, the key that looks like that, okay? And then press 20. Then press equal, and what do you get? How rich are you? 13,000 what? $34.21. Okay. Okay, I am your friend. Okay, now, okay. Let's do it monthly. What would be your amount now? Principal, 12,000 again. What do we put in here? 1 plus 0.03. That doesn't change, but what do we do? Divide by 12 and multiply by, raise it to 12 times 5, which is 60. Hope your calculators will do that. Okay. Punch away. See what you get. Hope it cracks 14,000. I'm not sure it will, but does it? 13,000. Okay. 13,000. $39.40. Wow, I'm so glad we went to monthly because I got another $5.19 in those 5 years. That's $1 a year. Whoa, I feel rich. Okay. Okay. Doesn't make a lot of difference there, but it makes a little, and I'll take any bit you give me. How about continuous? What would that be? A is equal to 12,000. There's your P. Raised to, times e to the, which is times 5. I'll write it down, 0.03 times 5. That's the number of years. That, by the way, is 0.15, right? So if you're going, you can let your calculator do that if you want to, but you be careful with it. Yeah, it'll do it, no problem. So 12,000 E, and when open parentheses, 0.03 times 5. Close parentheses, E. Look how much easier that is to calculate. I'm sure we didn't break 14, did we? 13,940. What? $42 and what's that? 1 cent. Oh, I'm glad they put that penny in there. Okay, and 1 cent. Okay, so I got another almost $3 more that way. Okay, from monthly to continuously in 5 years. Okay, that's about 60 cents a year or something like that. Okay, all right. See how that works? I'll go with continuous anytime. Number 1, I get a little more money, but number 2, it's easier calculation. That's pretty easy than all those parentheses and stuff. All right, let's see. Did they get it right in the book? 13,934.21, 13,939.40, and 13,942 and 1 penny. Okay. Then they're going to ask you to only invest 10,000 in the checkpoint, and your annual rate is 4%. Oh, that's better. And 7 years. Let's see how you did there. Okay. That's one example. Any questions on that? All right. Oh, here's how they show how you do it. Here we do quarterly compounding. N is equal to 4, 5 years. T is equal to 5, 3%. R is equal to 0.03. So we enter that in our formula there. And that would be 12,000 for P, 1 plus 0.03 for R, divided by 4 for N, 4 times 5 for your exponent. Okay, 13,934.21. Same thing for monthly, except now your N is 12. So you do the same thing except to 12 in the denominator and 12 in the exponent. Exponent wins and brings you up to a little bit higher, $13,939.40. And then when you do it continuous compounding, good old PERT, P times E to the RT, okay? 12,000 E to the 0.03 times 5, and that gives you $13,942.01. Use a calculator, okay. All right, that's the last slide in the set, but there's one more example, and this is a pretty important one. Radioactive decay. What are we meaning by that? Anyone know? Okay, yeah, something like that. Okay, when you hear radioactive, what comes to mind? Radiation? What comes to mind? Say again? It's explosion, okay? I thought you look like a violent crowd here, yeah. Okay, so let's say if someone were to use a nuclear bomb, and North Korea is talking about it, we've done it, with Japan. Guess what? That radiation hangs around what they call a half-life. In other words, it decays away, and you know how the decay pattern goes like this. So after so much of a time period, so much of it is left, and then less and less. guess what? It never completely goes away, but it approaches zero at some point. And what we base it on is what is called the half-life. How long does it take for half of it to go away? So here's our problem. In 1986, a nuclear reactor accident occurred in Chernobyl. Sad, sad story. And what was in the Soviet Union is now Ukraine. The explosion spread highly toxic radioactive chemicals such as plutonium, which is 239 plutonium, that's the atomic mass of plutonium, of this isotope of plutonium, over hundreds of square miles. The government evacuated the city and the surrounding area to see why the city is now uninhabited. The entire city is still uninhabited. That was 1986. That's been 14 and 17, 31 years. It's, well, in November it will be. Well, it doesn't say what year, month, okay. So 31 years, still uninhabited. To see why, here's the model. Okay, this is radioactive decay. P, okay. Now this P is the amount of plutonium, P for plutonium, that's still there. Is equal to 10, okay. That's from an initial amount of 10 pounds, so that's your initial amount, okay? Let's just say 10 pounds. After T years, that would be T times 1/2. That means the half-life is T over 24,100. That's the half-life of plutonium. So let's see. It says sketch the graph of this function over an interval from t equals 0 to 100,000. Okay, you want to do that by years? Let's not. Okay. Okay. Let's just pretend we did. Let's do 17. Okay? Let's do 17 years and see how much of that 10 pounds of plutonium is still there. So P is equal to 10 times 1/2 to the 17 divided by 24,100. Okay? You got your calculators. Punch away. Okay? Oh, by the way, we people in the South are a little violent. We punch numbers. In other parts, they press numbers. Never mind. Okay. 10 times 0.5, then do your caret key. Open parentheses, 7 divided by 24,100, close parentheses, equal. 7, 17. I'll say 7. I don't read well. Okay. What you get? 9.99. Wait. 9.99. Oh, 5.1. That's close enough. 17 years later, almost all 10 pounds are still there. Let's go up to 100,000 years. I don't think I'll still be around, but let's see how much plutonium will still be there. 10 times 1/2. Did everybody get that, by the way? Okay. They in the book did, oh yeah, they did 31 too. Yep. Wait. They got 9.991. Did I hear you say a 5 in there? 5.1. Did you get? Okay. How did they miss it so badly? Oh, wait. Where did I do 17? I meant to do 31 over 24,100. Sorry about that. That was 17 years later. Sorry, I was doing 2017. Let's do this one now. Sorry about that. I kept saying 31 and wrote down 17. I don't know. 991? Huh? Oh, 991. 31 years later, there's still almost 10 pounds of it there, radioactive. Let's do 100,000 years, okay? Maybe they can move back in after 100,000 years. Let's see. 1/2 raised to the 100,000 divided by 24,100. We'll show that plutonium, won't we? Second? 0.56. Okay. 0.56. What? One more maybe? Huh? Okay, let's round it to 4. Okay. There it is. Yeah, they put 0.564 pounds of plutonium remaining. Okay, maybe I can move back in 100,000 years. Okay. This sounds pretty extreme, doesn't it? It's not. Last year before, had a student in this class, this class actually. He started in my Math 100 class, and then he also took my Math 112 class. And he sat right back there in the corner every time. Nice kid, okay? But his parents from the U.S. had adopted him from Ukraine. And he couldn't have been even 20 years old yet, okay? He was missing an arm. Not an accident, except that accident. His parents, and close to 20 years after that, their DNA was still messed up, and he came out. He also had a hair lip. He had several other things and some developmental issues too. That many years, and they had evacuated. They had moved. And that many years later, still was affecting. And of course, when he was born with a deformity, they put him in an orphanage. They just left him. And fortunately, he got some really good, caring, loving parents here from Birmingham, went over and adopted him. And he was one great kid, okay? He was at Jeff State in physical therapy technician because he wanted to help other people who had physical disabilities. I hope he's working now. Those courses he needed to graduate, and hopefully he is. He went deep sea fishing. His dad took him there. He learned to golf with one arm. He did as much as he could, and just had the best attitude of just about any one of it. He struggled with math because I think some developmental issues, but he still, overcame an awful lot. So this isn't just a made-up problem. This is a serious thing. No one's going to live in Chernobyl, Ukraine for centuries at all. Not a minor thing. So that was a nuclear disaster, not the bomb. Who knows? I don't even want to know what's the result in Japan, how many people are still showing up with problems there. There probably are still some. And we did that, okay? Now, on the other hand, I had half of a kidney removed several years ago. It was a angiomyolipoma, which was just angi means blood, myo means muscle, and lipoma is fatty tissue. So it was just a thing growing on my kidney. Okay, wasn't benign. It was benign. It wasn't cancerous or anything, but it was growing on the kidney and getting bigger. Okay. So they said, we got to take it all out because it might rupture and then we wouldn't be able to get you to the church on time, so may not. So they took it out. They went stem to stern. I mean, I said, how many people do you have in there anyway? Yeah. Afterwards, they wanted to check and see how good it was less than half the kidney, how good it was functioning. So they put me on a table, injected me with a radioactive material with a much shorter half-life than that, and then they measured the blood flow, the body started taking it out of the blood, and they measured the radioactive decay of that, or how it was doing because it was emitting radioactive. So nuclear medicine basically is using radioactivity too for a very positive purpose. So it's not just blowing up power plants and stuff, it's other things as well. Boy, that is a scary looking graph if you look at the one on 207. All right, let's move on. 3.1 exercises. Vocabulary. Polynomial and rational functions are example of what kind of functions? This goes back to the very beginning. page 200, the first bold word in the text. Polynomial and algebraic functions. Those are algebraic functions. Exponential and logarithmic functions are examples of non-algebraic functions, also called transcendental function. That's not sitting in a corner going, no, that's something else. Okay. So, number 3, you can use the blank property. Oh my goodness, look at this. They keep it coming. Okay. I'm sorry.
Can you check the time? I have to be in the NASA lab, and after you finish, I would like for you to sign off and say that I got here at a certain time. Because she tells me that it has to be like you or somebody else that I don't know that can validate.
Okay. Okay. Just come down there and sign you in. Is that what you're saying?
Mm-hmm.
Okay. All right. Okay. Number 3, you can use the blank property to solve simple exponential equations. One-to-one property. Very good. Okay. Glad you remembered that one. Okay. That you can find on the bottom of page 202. The exponential function, f of x equal e to the x, is called the blank blank function because the base e is called the blank base. A lot of blanks there, aren't there? Top of page 204. Kind of in reverse order. Natural exponential function because e is called the natural base. Very good. Okay. To find the amount A in an account after T years with a principal P and an annual interest rate R compounded N times a year, use the formula A is equal to 1 plus, P times, P times. Got it. Okay. To find the amount A in an account after T years with the principal P and the annual interest rate compounded continuously, you can use the formula. Okay. A equal P e to the RT. Got it. Okay. Homework exercises here. Do any of the odds 7 through 11. And I would do, and I think I told you this before, I would do all of 13 through 16, but the answers for 13 and 15 are in the back. Okay? Then do any of the odds 17 to 21, either 23 or 25 or both, 27 or 29 or both, 31 or 33 or both, 35 or 37 or both, 31, any of the odds 39 to 43, 45 to 49, either 51 or 53 or both, 55 or 57 or both, 59 or 61 or both, and then any of the odds, especially if you're a trust fund kid, number 63, but no, any of the odds 63 through 71. And these are pretty good problems. You'll see other exponential things, your trust fund, inflation, computer viruses, population growth, radioactive decay, depreciation, drug concentrations. There's all kinds of things, very practical things. True, false, you might look at number 73, know why that's true or not. And then you might try 75 or 77 if you'd like. You figure that out. You can look at the others if you wish. Actually, 85 is a pretty good problem just to think through. So let's move on from there. All right. 2. .2. Well, if it'll ever load. Here it comes. Oh, PowerPoint is so fast. I love this program. It's now opening at 0%. 20. Okay, it got up to 90%. But that's not enough. It's got a price. Ah, there we go. All right, from current slide. Okay. Still functions and exponential logarithmic functions. 3.2 deals with logarithmic functions and their graphs. All right. Recognize and evaluate logarithmic functions with base A. Graph logarithmic functions. Recognize, evaluate, and graph natural logarithmic functions. Okay? Not A, but natural. Okay? And use logarithmic functions to model and solve some real-life problems. Let's talk about what a logarithmic function is. Every function of the form f of x is equal to a to the x. What kind of functions do we call those? Last section. Exponential function with base a. Passes the horizontal line test, remember? They're all going like this or they're all going like that. They're either all increasing or all decreasing. So therefore, if they pass the horizontal line test, they're one-to-one functions, pass the horizontal line test, they must have an inverse. Remember, inverse functions happen anytime functions are one-to-one, which means they pass the horizontal line test. And these do it everywhere. This inverse function is then called the logarithmic function with that same base a. So here's the definition. For x greater than 0, okay, never try this with x 0 or less than 0, okay? A greater than 0, your base has to be a positive number too. Don't use 0, but never, again, don't use 1 either. Remember, your bases can't be 1. But x is greater than 0, a is greater than 0, but a can't be 1. X could be, but it's fine. Okay, y is equal to the log subscript a, that means the log base a of x. That statement is true if and only if, this is how you do inverse functions, x is equal to a raised to the y power. The bases stay the same, you exchange your x and the y. Here the y is the dependent variable, x is independent. Here y is the independent variable and x is dependent. So this is how they're related. Here's your exponential function, here is your log function. The bases stay the same and you exchange the variables. So the function f of x equal log base a of x is read the log base a of x, okay, like I just said. It's called the logarithmic function with base a, okay? So these two equations, y is equal to log base a of x, is equivalent to x is equal to a raised to the y power. These are what we call equivalent functions. One undoes the other. They are equivalent. The first equation is in logarithmic form, the second in exponential form. For example, 2 is equal to log base 3 of 9. Okay? Rewrite that as a equivalent exponential function. 9 is equal to what?
3 squared.
Hey, we knew that, didn't we? Okay, so that's just undoing what you just did. Exactly. Okay, what is that? Rewrite that. Say again? Okay, a little louder. No, the 125 is already equal. So they reverse the sides on you too. So you do it the other way.
3.
No. 3. Oh yeah, you're right. Go ahead.
3 equals log 5.
Base 5
Base 5.
of 125. That's it. 3 is equal to, and they reverse the sign again. 3 is equal to log base 5. Be sure you always have the same base of 125. See, that's the dependent, that's the independent. Now this becomes dependent, independent, that becomes dependent.
So when you're going from exponential to logarithmic, the base becomes the subscript.
Yeah, the base is the subscript. You're absolutely right.
Okay.
Yeah, I may have pointed to the wrong thing there, but yeah. The base is always the base. Base here is there, the base there is there. The base of an exponent is the base, and the base of the log is the subscript. Yeah, you got it. Okay. Good deal. When evaluating logarithms, remember that a logarithm is an exponent. Now that sounds bizarre, but it is true. That means that the log base A of x is the exponent to which A must be raised to get x. Yeah, okay. So here's the example of that. Log base 2 of 8 is equal to 3. Is that right? How's the other way to write that? Eight is equal to 2 cubed, exactly. Because 2 raised to the third power is 8. That's exactly right. Okay? So evaluate each of these logarithms at the indicated value of x. Okay? Now, frankly, I would do it just like we've been doing it. Rewrite that into an equivalent form. Okay? So let's do it. Oh, wait. Oh, okay. So x is equal to what? They said it's 32. How'd they get that? X would be equal to 2 raised to the, okay, right now, okay, all right, okay, yeah, let's back off a minute here. Oh, the eraser didn't back off. Okay, let's name this, I think it'll help you to do it this way. Let's name this Y. Yuck, the pen didn't come back. There we go, okay, let's name this Y. And they say x equals 32, okay? So rewrite this one. And what would that be? X, which is 32, equal 2 raised to the y power. Now, you figure out what that y is. Two squared is 4. 2 cubed is 2 to the 4th power is, and 2 to the y is equal to 5. You got it. So that would be y is equal to 5, or f of x is equal to 5. I just find y is easier to work with than f of x. Okay? You do b. Y is equal to log base 3 of x when x is equal to 1. So rewrite that. 1 is equal to 3 to the y. Y must be 0. You're absolutely right. That's the only way you can get 1 out of that. Okay? Let me erase some stuff here. Okay? And how would you do that one? Y is equal to log base 4 of x. X equal 2, so what would that equal? Okay, 4 to the y, right? Because that's your base. Y is now that. And 4 raised to what power is 2? It's the square root of 4, which would be y is equal to 1/2. Perfect. How about the next one? Y is equal to log base 10 of x, and rewrite that. X, which happens to be 1 over 100, is equal to 10 to the y power. Second? I don't think so. Okay, let's rewrite this as 1 over 10 squared. Is that right? Isn't 110 squared is equal to 10 to the y? Rewrite this with 10 as the base. If you move something from the denominator to the numerator, what do you do to the exponent? Negate it. Now can we figure? Oh, yes, okay. What? Y is equal to -2. All right. I know we're running out of time. Sad but true. Day you've been dreading all term. Let's just see their answers quickly. F of 32 is equal to log 32, okay. Because 2 to the 5th is equal to 32, that's equal to 5. I prefer putting a y in there. It makes it easier. But that's what we got, wasn't it? Okay. And that gave us a 0. What's that? Yeah. This is the last stuff on the test. Okay. And f of 2 is equal to log of 2. Because 4 to the 1/2 square root of 4 is 2. Your y is equal to 1/2. Okay. And this is the one we're just struggling with. And because all that's true, and we backed it up just like that, that gave us y is equal to -2. Okay? Now, I wish we had time for this. This is such good stuff, but we don't. So we'll stop there and make sure. Yeah. Okay. Good deal. So just a quick reminder, do your student course evaluation. Please get those done before the end of the term. Oh, yeah, let me give your papers back to you. Someone already walked out without the papers. Shame on them. They'll get arrested because they don't have their papers. Okay. I didn't say that, did I? Not out loud. Okay. Oh, I know who left, and it was good she left. Okay. I'm sorry, that didn't sound right, did it? Okay, Brianna never showed, did she? Justin? Here's your quiz 1. Jonathan? 2. Did show today? Yeah, there he is. Nathan didn't. Amber did. Michelle did. You wrote me a book. Okay. I'm sorry. Yolanda not here, and Amber. Ashley's here. Okay. That's quiz 1. Now, I can't say for sure no one's going to turn in quiz 1 again. A few people haven't turned it in, so please don't let these get out. Otherwise, guess what? Your grade gets diminished because they see the correct answer. So watch that. Brianna's not here. Justin is. This is your test 1. And I know there's a couple people who haven't done test 1, so please don't let these get out. Okay? Akira, Allison, Amber, faithful are here. Ryan, Terrell, Nathan not, Amber Reese, yes, and Michelle. Sorry. Oh, okay. And Ashley. There's your test 1. All right. And like I say, I know some people haven't finished test 1, and there are some legitimate reasons. So, Brianna's not here. Justin, this is your quiz 2. Jonathan, and again, I'm sorry that we didn't get to answer questions, but because some people had taken it, I couldn't answer any questions yet. So come see me. I'll be here today, Birmingham tomorrow, here all day Monday. Okay. Alexis, Allison, Amber, Ryan, Okay, now some people left not finished on there, so I'm gonna check grades before I pass it out. Yeah, I put yours on, so Justin, I'm pretty sure I put, Jonathan. Pretty sure I put Arcuros. Yeah. Okay. Alexis, I'm pretty sure I put yours. And Allison. And Amber. And Ryan. And Terrell. Nathan's not here. Amber is. Put yours down, I think. And Michelle. Okay, and Ashley. I'm sorry. You got it. All right, and we'll see everybody bright and early Tuesday, if not before. Good deal. Will anyone see Natalie? She left early. I got some of her stuff. So, okay, that math program that Dr. Thomas is doing? Okay, now there's a couple of things. One is the thing that Dr. Briggs runs over, and it's on both campuses, but he's mostly on Birmingham, but he does a lot of stuff over here. Are you ever on Birmingham campus? It's called the Summer Enrichment Program.
Yeah.
Okay. Oh, that's the one you want, not the one for young girls.
Not young girls.
Oh, okay, right. Okay. Okay. The Summer Enrichment Program is Dr. Briggs. If you are on Birmingham campus, son, or you can be.
Not really, but I work close there.
Okay, right. We'll go by there. In fact, if you want to give, I can't guarantee. I'll probably see them tomorrow.
Okay.
So if you want me to just tell them you're asking, or you want to get in touch with his email is cbriggs@bostonstate.edu.
Okay.
And he's in charge of it. He can answer everything about it.
Okay.
Okay. Yeah. All right. Let me shut this down.